Now we take application number 3, that is electric field due to a uniformly charged sphere. So this time, instead of shell, we have a whole sphere, and that is charged uniformly. It has a uniform charge. Total charge is Q, and it has a radius capital R. But then, if I think that whether this sphere, which is having a uniform charge distributed within this whole volume, would be a conducting material or an insulating material. So my answer is it has to be an insulating material, because for a conductor, for a conducting material, the charge will only remain at the surface. So if it was a conducting material, then charge would have only remained at the surface, because charge is distributed in this whole volume. So it is an insulating material made up of some dielectric. That's why the charge is not moving out. So charge is uniformly distributed in the whole volume, and it has radius capital R, and we want to find electric field due to this charge at a point P outside, maybe at a distance R. Maybe in the second step we will find the electric field and potential at the surface, and also we are interested to find electric field and potential inside. So first outside. This is not much change. The only difference will be, if earlier in the previous case of shell the charge was distributed on the surface, there you are having surface charge density, this time you will have a volume charge density. So if I am looking for what is volume charge density, volume charge density, which can be represented as rho, it will be Q by 4 by 3 pi r cube. Total charge is Q, total volume is 4 by 3 pi r cube. So again I come back to my expression, I want electric field outside, electric field and potential outside. So for that, step 1, you know very well, assume a Gaussian surface. Now the Gaussian surface would be a sphere of radius small r. So it would be a sphere of radius small r. Step 2 says that point P lies on it. Step 2, there we look for the electric field. Look for direction of electric field. So due to this positive charge, yes, the electric field would be radially outward. It will be radially outward. And then what is step 3? If I say, what is step 3? You know it. Take a patch on every kind of surface. Now, the only kind of surface is spherical here, just one kind of surface. So I take a patch on it. ds, same is the direction of electric field. So we take a patch on it. So we say d phi is what? E dot ds. D phi is E ds cos 0. So d phi is E ds. And then we say total flux. Total flux will be integration of d phi. So it will be E into integration of ds. So the total flux will be E into 4 pi small r square. So take a patch on every kind of surface and find net flux. Now other point, step 4, look for the charge inside. It is almost same what you have done in shell, charge inside, whole charge Q is inside. So charge inside would be capital Q only. Now what? Step 5. And in step 5, you apply Gauss theorem. So in step 5, we will apply Gauss theorem. Which says net flux is equal to charge inside by epsilon naught. So net flux is E into 4 pi r square is equal to charge inside Q by epsilon naught. So you have electric field which is 1 by 4 pi epsilon naught Q by r square. So I am looking at this result once again. You have the charge Q distributed everywhere. It has its own radius capital R. You are looking for the electric field at a point at a distance R. The electric field there comes out to be 1 by 4 pi epsilon naught Q by R square. So can we say Q behaves as though whole charge situated at center? So it behaves, or the arrangement behaves as though whole charge is situated at center. So it is like as the whole charge capital Q was not distributed uniformly, as though the whole charge Q was somewhere here as a point charge. And that's why the potential with the same concept will be written as 1 by 4 pi epsilon naught Q by R. This is for outside point. Yes, we can introduce all these values in terms of volume charge density. The volume charge density was total charge by 4 by 3 pi r cube. So Q can be written as 4 by 3 pi r cube into rho. So this electric field can be written as 1 by 4 pi epsilon naught 4 by 3 pi r cube rho divided by r square. So you will have its value 4 pi gets cancelled. So rho r cube by 3 epsilon naught r square. And the electric potential can be written as rho. Here it will be r instead, so rho r cube by 3 epsilon naught r. So in case if you are interested to write in terms of volume charge density, you can write like that also. So I am sure it was very easy for you. Now you know what is next step to look for electric field and potential at the surface. And again, it is going to be very easy for you at surface. Electric field and potential at surface. So here once again you have this charge sphere and you wanted to get the electric field and potential at surface. Maybe you have a point M here for which small r is equal to capital R. So you will follow the same steps. The first step is you will assume a Gaussian surface which will be a sphere of radius capital R itself. You will assume a Gaussian surface which will be a sphere of radius capital R itself. Then you will look for the direction of electric field which will be radially outward. You look for the direction of electric field which will be radially outward. Then you will take a patch on every kind of surface and then you will find the flux through it, E ds. This is ds and here is electric field, E. So the flux through every kind of surface will be E dot ds. The flux through will be E ds cos 0. So the net flux will be E integration of ds. So the net flux will be E into 4 pi capital R square. So you obtain the flux through this assumed Gaussian surface. And next step, charge inside. So when you look for the charge inside, it is Q. The whole charge is there within it. Or you can also call it rho into 4 by 3 pi r cube. And then you have the net flux, you have charge inside, you apply Gauss theorem. So when we apply Gauss theorem here, we can say E into 4 pi r square is equal to Q by epsilon naught. So electric field is 1 by 4 pi epsilon naught Q by r square. It will behave as though the whole charge is situated at center. And similarly, the potential also will be 1 by 4 pi capital 4 pi epsilon naught capital Q by r. It will behave as though the whole charge is situated at center. So this is electric field and potential at surface. Now interesting is how to find electric field and potential within it. So let's take electric field inside charge sphere. Inside charge sphere. So here you have this charge sphere. It was having a radius capital R. You are interested to find electric field at a point P inside. You will assume a Gaussian surface, which is a sphere of radius small r. You will look for the direction of electric field. Electric field will be obviously mainly due to the inside charge only. So the direction of the electric field here will be like this. We can take it outward. Then you will take a patch on each kind of surface. So let's take it like this. Its area vector is here. Electric field in this direction. So the flux through it will be E dot ds. The flux through it will be E ds cos 0. The total flux through will be E into ds. So the total flux will be E into 4 pi small r square. But next comes the most important point, that is charge inside. Now charge inside in this case is the charge which is within this. It has its own whole radius capital R, but we are only talking about radius small r. So charge within, should I call it rho, volume charge density, into 4 by 3 pi small r cube. It is not rho into 4 by 3 pi capital R cube, it is rho into 4 by 3 pi small r cube. We are only interested in the charge inside this. This outside doesn't matter. So let's apply Gauss theorem here. Which says net flux is equal to charge inside by epsilon naught. E into 4 pi r square is equal to rho into 4 by 3 pi small r cube by epsilon naught. This 4 pi gets cancelled, capital R square only 1 r. So the electric field is rho r by 3 epsilon naught. So electric field within this is important. It is directly proportional to r, where rho is the volume charge density. And let's write the expression for electric potential. Now I'll be directly sharing that formula for electric potential within. We are not proving it like earlier we have done. The potential within will be 1 by 4 pi epsilon naught q by 2r into 3 minus r square by capital R square. Now this result I am directly sharing with you. What is more important is the outcome. Now in this arrangement, for small r equal to 0, it means at center. The potential will be 1 by 4 pi epsilon naught 3q by 2r. This is at center. And for small r equal to capital R, this is at surface. At surface, capital R square by capital R square, so this is 1. So the potential at surface will be 1 by 4 pi epsilon naught q by r, 2q by 2r. So can we say potential at center is 1.5 times the potential at surface? In a shell, the potential was same everywhere within. But here, in a uniformly charged sphere, the potential is more at center and it is reducing towards the surface. And then after it is, yes, it is inversely proportional to 1 by r. It behaves as the whole charge is situated at center. So from all that, I plot now graph showing the variation of electric field